All right, guys, so we're looking at the exponential functions. Functions in the form of f of x is equal to b to the x power. When we talk about the exponential functions, guys, what you have to realize is that the base cannot be equal to 1, and it cannot equal to 0 either. The base cannot be 0, and it definitely cannot equal to 1, because 1 raised to any power gives you 1 right back, and 0 raised to a power doesn't lead anywhere, guys, okay? So an example of an exponential function might look something like this, guys. And normally, if I had sufficient time, I would go into a long, elaborate explanation of most of this. But because we're under the time constraints, I am going to cut back on some of the information, but I'll make sure to give you what's really, really necessary, guys. So when we look at an exponential function, we're looking at a function of the form f of x equals to 2 to the x. What you will notice is that the variable is no longer the base. The variable is actually the power. For these exponential functions, guys, you will notice two types of exponential functions. You will notice a growth function. We'll talk about the graphs very shortly, as well as a decay function, a growth and decay function. And we'll talk about both of them. When we talk about the domain of the exponential functions, whether we're talking about growth or decay, guys, the domain is all reals. So when you express this in interval notation, it would go from negative infinity up to positive infinity. Likewise, guys, the range is what you need to be careful with. The range of these exponential functions, you need to be careful, whether it's growth or decay. The range, like I said, be careful, is going to go from 0 up to positive infinity, okay? So when we talk about these exponential functions, guys, we're looking at things that multiply very rapidly. Either they grow very rapidly or they decay very rapidly. So once again, we got exponential growth, where it mimics scenarios in real life that grows or multiplies very rapidly, or exponential decay, which mimics those scenarios in real life where they are decaying or they're depreciating, they're decreasing exponentially. Guys, I'm so excited. You guys don't know how excited I am. Every time I watch television these days and I'm looking at all these exponential graphs, looking at the coronavirus, guys, the coronavirus. And especially recently, because, you know, we're going into the cold season and the numbers are increasing, we're looking at these beautiful exponential graphs, guys. So what in the world am I talking about? So let's go ahead and look at this basic example right here, okay? Just to expedite the process, guys, I am just going to go ahead and plug in some values in here, okay? -3 values for x, and we're going to find the corresponding y values. -2, -1, 0, 1, 2, 3, and maybe we can go to 4, okay? Let's see if we could plug a 4 in there. I don't think the 4 is going to work, but at least we're getting to 3, guys. So we're going to go ahead and create this chart for this exponential function. Now, rather than starting at -3, I am going to start at 0, guys. If I plug in 0 into this function for x, I end up with 2 to the 0 power. 2 to the 0 power, anything raised to the 0 power is equivalent to 1. So 2 to the 0 power is 1. And then if I take 2, raise it to the first power, I will get 2. If I take 2, raise it to the second power, I will get 4. If I take 2, raise it to the third power, that will give me 8. You know what? I'm going to squeeze the 4 in here. 4 will take me to 16, guys. I don't know if you can see it because it's not showing up on my screen, okay? Now, I'm going to go backwards. When I plug in a -1, guys, into the function for x, I get 2 to the -1 power. Whenever you encounter these negative exponents, listen to this carefully, guys, because you're going to see it again later on, okay? Whenever you encounter these negative exponents, think of a fraction. 2 to the -1 power is indicating the reciprocal, guys. So this is actually 1/2. So a negative exponent indicates a reciprocal, so that 2 to the -1 power is actually 1/2, okay? So likewise, if we have 2 raised to the -2 power, we take the reciprocal, so this would become 1/2 squared. And 1 over 2 squared becomes 1/4, okay? And then finally, the -3, 2 to the -3 power gives you 1 over 2 to the 3rd power, which is 1/8. So I want you to notice something, guys. The smaller the value of x gets, what's happening with the value of y or the value of the function? The function seems to be approaching 0. Remember earlier, I mentioned that the range of this function is from 0 up to positive infinity, but 0 is not included, guys. This is why. As the values of x are decreasing, the values of the function approach, okay, 0. So when you sketch the graph of this, guys, let me go ahead and sketch the graph out for you. I am going to go to the XY plane so I can go ahead and sketch it out. This is what the graph is going to look like, guys. Okay, let me try and squeeze all of this in here. My space is limited, but again, I am going to try and squeeze it in, okay? So 0, 1, guys, that's your y-intercept right there. So every one of these exponential functions, guys, will have a y-intercept at 0, 1. So you might want to write that on the side. Y-intercept at 0, 1, okay? 0, 1. You plug in 0 for x, solve for y. Next, guys, when x is 1, y is at 2. When x is 2, y is at 4. When x is 3, y is at 8. And then 4 would be somewhere way over here. Now, let's go on the opposite side. When x is -1, you're at 1/2. When x is -2, you're at 1/4. When x is -3, you're at 1/8. So guys, what do you notice? The graph is getting closer and closer to the x-axis, which is the equation, okay, of y equals to 0. So in other words, guys, this graph has a horizontal asymptote at y equals to 0. This graph will never intersect the x-axis because there is no way, guys, to take 2 and raise it to some power and get 0. That is impossible. So be careful with the exponential growth functions, guys. Now, what I want you to think about for me is this, guys. For the exponential growth function, what are some things in real life that mimic exponential growth? What are some scenarios in real life that mimic exponential growth? You guys can go ahead and drop it in the chat, and then we'll talk about the decay. What are some scenarios in real life that mimic exponential growth? Just throw some out there, guys. Anybody? Oh, Shazam. Nobody? The virus. I love it. The coronavirus. The Rona, yes, it does. The infection rate of the coronavirus, yes, mimics exponential growth. Yes, Maddie. Stocks, or in this case, I'm going to go ahead and put it out there, money. There's also population. Let me see. Did somebody say population? Let me see here. Somebody put something else in there. Stocks, the stock market. Okay, good. All right. So population, guys, is another one. Population of the human race. Population of bunny rabbits. Population of ants. Ants outnumber human beings, okay? Later on, we'll talk about exponential growth in regards to money. But for now, guys, I'm going to pause and take a look at the exponential decay function. When we talk about the exponential decay function, we're looking at equations of the form 2 to the negative x power. Now, remember I told you earlier to keep in mind that when you notice a negative exponent, guys, what should you be thinking about? A fraction. Well, this one happens to have a negative exponent. So this means this is actually a fraction. So 2 to the negative 1 power, we just figured out, is 1/2. So you can take this and rewrite it as f of x equals to 1/2. And then the 1/2 is the same thing as 0.5. So guys, all three of these would mimic exponential decay. Now, I know what some of you are going to be saying. Well, how can I tell the difference between an exponential growth and an exponential decay? So these are the exponential decay function. The exponential growth function was f of x is equal to 2 to the x. How can I differentiate between growth and decay? So for the growth function, guys, you're looking at the base, whether it's the exponential growth or decay. To determine whether you have a growth or decay, look at the base. If the base is greater than 1, then it's indicating you have a growth. Now, if the base, though, is less than 1, but greater than 0, we're indicating an exponential decay. So in other words, if it's a fraction, guys, it is an exponential decay. But sometimes you can't tell if it's a fraction, so you just got to know that, okay, whether or not the number is less than 1 or n greater than 0 to determine if it's an exponential decay. Now, for the exponential decay graph, guys, remember it's decaying, so it's decreasing over time. It still has a y-intercept at 0, 1, and over time, the graph decays and it gets closer and closer to the x-axis. So the graph of the exponential decay function will look something like this, guys. Now, I could do a chart for it too, but unfortunately, I don't have enough room, so that's why I'm not going over it. But for the y-intercept right here, that's very easy. You plug in 0 for x, guys. Anything raised to the 0 power, that's equivalent to 1. I mean, if you were to plug in 1 in here into the function, 1/2 to the 1 power, that gives you 1/2. 1/2 to the second power is going to give you 1/4. 1/2 to the third power is going to give you 1/8. So that's these values over here. Now, if you were to take a half, you raise it to the -1 power, guess what that's going to give you? A +2, guys. Yeah, so be careful with that. So exponential decay, it decreases, let me write this down for you. It decreases from left to right, whereas the growth, guys, was increasing from left to right. So as the values of x gets larger and larger, the values of the function, the values of the exponential decay function gets closer and closer again to the x-axis, all right? And the domain and the range, guys, remains the same. So here's my next question to you guys. What are some scenarios in real life that mimics the exponential decay graphs, guys? What are some scenarios in real life that mimics exponential decay? Anybody? Drop it in the chat. Oh, look at you, Brian. Half-life. The half-life of a drug in your body, like Xanax or something like that. Or should we talk about the half-life of, I'm gonna go ahead and put it in there, guys, because, you know, people are just talking about legalization, so we might as well, medical marijuana, okay? And it works for some people. Yeah, the half-life of that. After a certain period of time, how long does it take for it to just dwindle out of your system, okay? Nicholas is saying something. Let me see what Nicholas is saying. Right now, movie theaters are experiencing a decay. Okay, I'm sorry. That's a good one, Nicholas. I love it. I love it. Yes. Death, loss of income. Yes, absolutely. So guys, yes, money could fall under exponential decay, but most of the time when we think about money, we're thinking of appreciation, not depreciation. By the way, talking about depreciation, one of the most basic things when it comes to depreciation and decaying, guys, decaying over time, the value of something depreciating over time has to do with the value of a new car. The minute that new car is driven off the lot, it starts depreciating in value. So perfect example of exponential decay. Population is another one, like the population of a creature that's going extinct, okay? So something like that. But yeah, great examples, guys. I love the examples. Keep them going. So guys, let's get into it now. We're going to get into what we really need to get into. Normally, I would also discuss the transformations with you, Do you guys want me to briefly talk about the transformations? Because I know some of you might be heading up to pre-calculus later on. No, yes, no, you guys are good? No transformations? Okay, all right. So I'm gonna leave the transformations alone, okay? You know what? Maybe I should briefly mention, let's briefly mention, okay? For the transformations, guys, briefly, I'm not going to linger in this. You just need to be aware of this. When we have an exponential function, guys, f of x is equal to b to the x, if we add a value out here, that c value, it moves the graph, it shifts the graph up or down in the same direction. Now, if this is happening in the exponent, okay, if the c is happening in the exponent, the c value is going to move the graph left or right in the opposite direction, okay? Opposite direction. Now, on the other hand, if you've got f of x is equal to a negative b to the x, this will reflect over the x-axis. But if the negative is in the exponent like we saw earlier, it's going to reflect about the y-axis over the y-axis, okay? And then last but not least, this is the last one I'm gonna mention, guys, and that is the vertical stretching and shrinking. So here, when you have a leading coefficient here, remember, if the leading coefficient is greater than 1, it is stretching vertically. Now, if the leading coefficient is between 1 and 0, it is going to be shrinking vertically, all right? So guys, those are the transformations in a nutshell. It's good to be aware of them, especially if you're moving on to the higher level math courses. But let's get to the real part of this. And the real part of this, guys, happens with compound interest. This is one of the greatest formulas, guys, you will encounter in a math class. Right there, compound interest.
Excuse me. Can you just go back very quickly to the transformations slide? I didn't finish the last section that you wrote.
Okay, let me see if I can recall it. I might not be able to recall it.
And if not, you can. I'll just wait till the end of the recording.
Okay. Okay, it's taking me a long time. All right. All right. So let me go ahead and keep going, and then you can watch it over again. By the way.
Yes.
Okay.
You're right.
And that's not the critical part of the lesson. Okay. So compound interest, guys. This, like I said, one of the most important formulas you will ever encounter in a math class. When we talk about compound interest, this is interest. By the way, guys, why do we invest money? Anybody?
For profits.
Yes. What else? For it to grow. Absolutely, guys. Exponentially. All right, guys. So when we talk about compound interest, we're looking at interest which is accumulated on the principal and on any interest earned and on any earned interest. In other words, your interest is compounding, guys. So not only are you earning interest on the principal, you're also earning interest on any interest you earn. So then your interest is being compounded. Compounded is just another term for calculating, okay, guys? So anyways, we invest money, guys, so we can make more money, so our money can grow, yes, Jennifer, exponentially, okay? So guys, the formula to calculate compound interest is this, and I'll go over the variables with you very shortly, is A equals to P times 1 plus R over N to the NT power. This is the most important formula in mathematics.
What does that last part say? Is this and interest?
Okay.
On any something and interest?
On any earned interest.
I think you put a couple extra letters in there.
I did. Let me see if I could erase that and try that one more time. you know, sometimes I get a little excited and I just keep going on and on and on. I think that's what I meant to write, okay? On any earned interest, okay? So guys, this is the formula. I don't care what anybody else tells you in mathematics, this is the greatest formula in mathematics, because this is the formula that's used in real life to calculate how much you're earning on your investment. So let me go ahead and clear this out so I can define some of these variables, guys. Okay, A is the total account value, or the total amount in the account. Now, P, by the way, these stay consistent. For those of you moving on to, let's say, MGF 2107, you will see the same formula all over again with the same variables. P represents the principal. That's your initial investment. T stands for time, and the unit of time is year. So if they give you like 6 months, guys, you got to convert it. And of course, R represents the rate. The rate is in percent. You got to convert that to a decimal. Now, last but not least, you have the variable N. N is the number of times the interest is compounded per year. So I'm going to call this the compounding frequency. How frequently is the interest compounded per year? The interest could be compounded annually. If it's compounded annually, all the N values will be equal to 1. So guys, if you have this formula right here, A equals to P times 1 plus R over N to the NT power, N times T power, and you plug in 1 for every single N, the formula will simplify to A equals to P times 1 plus R to the T power. So once again, because the N value is equal to 1, okay, all the ones will simplify out. So you end up with a simple formula to calculate the compound interest, okay, or the total value of the account if the interest is being compounded annually. That's once a year, guys. All right.
So if you get like a quarterly statement for your taxes, then it's usually, the N would be 4?
Yes.
Probably.
Yes, absolutely. So there's also semi-annually. Semi-annually, meaning the interest is compounded twice a year, every 6 months. There's quarterly, and quarterly is where the interest is compounded 4 times per year. There's also monthly. Monthly is where the interest is compounded 12 times per year. And then last but not least, they have daily. But once you get into daily, guys, you might as well switch it over, okay? 365. In some textbooks, they like to use 360 because it's easier to use the 360 to do the calculations. Now, the best way to compound the interest on an account, guys, is where the interest is being compounded continuously. When the interest is compounded continuously, this means that they are calculating the interest all the time. So the formula we use for that, because we don't have an N value anymore, is A equals to P times E raised to the R times T power, AKA the PERT formula. So guys, for the PERT formula, you will notice you have that E value in there. It's a value, it's not a variable. It's an irrational number similar to pi, and it stands for 2.718. You do not have to memorize this. This is on your calculator. So if you go above the LN key on your calculator, you will notice the E button above the LN key, okay?
So can I just ask a quick question? The formula here, does it matter that A is capital and the other ones are all lowercase?
No, it doesn't make a difference.
Okay. And this formula, the PERT formula is what again?
When the interest is compounded continuously, when they're calculating the interest all the time. Unlike the previous formula, we had a certain number of times per year the interest was being calculated per year. But here, There's no number. It's just being calculated all the time.
So that is P times E, and then R and T are exponents?
Yeah,
Okay, I just want to make sure I write it correctly. Thank you.
times e raised to the RT power. All right, guys. So, guys, listen. Here's why this formula is so critical. With compound interest, your money grows faster. And then along with that, one of the most precious commodities you have when it comes to investing is time. So essentially, the earlier you start investing, the more you will accumulate in these accounts. So time, guys, is a precious commodity. Plain and simple as that. So essentially what I'm telling you is, if you're really, really young right now, you're in this class, because some of you, you're not even 20 years old yet. Time is on your side. So this is the prime time for you to start investing towards your retirement, towards your financial goals, whatever your financial goals might be. So let me go ahead and drop an example here, guys. Let's say you have $2,000 and you go down to the boulevard and you want to drop this in a savings account. The first question you're going to ask is, what is my interest rate? You don't need this money for 3 years, okay? 3 years, you don't need the money, okay? So you're going to drop it into a savings account. First question you should ask is, what is my interest rate? Guys, I'm not kidding. If I have some bankers in the classroom, you can go ahead and let me know. All right. So guys, the interest rate on most of these accounts are like 0.01%. The interest rate on these savings accounts, they're horrible. Now, you could get a better interest rate if you go to an online bank. And one way to check out the online banks is to go to bankrate.com, which will list various banks for you along with their interest rates on various accounts like a CD or a savings account and so forth and so on, okay? But for the most part, guys, the interest rate on these accounts are horrible, okay? So let's say you find a bank that's generous, a credit union. Credit unions tend to give you a better interest rate on your money. They're giving you 2% on your money. You leave this money in there for 3 years, guys. Let's calculate how much interest, simple interest. If we're just calculating the interest on the principal, how much would we earn in interest? Okay, in interest, we take the 2,000 multiplied by the rate, which is 0.02, multiplied by the time, which is 3. So you go ahead and throw this on a calculator, guys. 2 times 2 is 4, 4 times 3 is 12. So that's $120, okay? And so at the end of the 3 years, your account would have $2,120. If you're going based on simple interest, and simple interest is nothing more than interest earned on just the principal. Now, we're gonna switch it up. It's still the same $2,000, but this time we're going to compound the interest annually. We're going to compound the interest annually. So if we're going to compound the interest annually, guys, remember the formula simplifies to A equals to P times 1 plus R raised to the T power. So I'm just gonna go ahead and plug in these values into the formula, grab my calculator and plug it into my calculator exactly like I see it, guys. By the way, when we take the test, guys, in the classroom, you will be given the formulas, so you don't have to worry about memorizing the formulas. The formulas will be provided to you, okay? As well as on the final exam, everybody. 1 plus 0.02, close the parentheses, and then we're gonna raise this to the 3rd power, okay? So $2,122.42. By the way, make sure when you're rounding accordingly. This is money, guys, so 2 decimal places when nearest 100th, okay? So guys, what do I want you to notice? Here's what I want you to notice. When the interest is compounded just once a year versus simple interest, you've just earned yourself an extra $2.42. Through the power of compound interest, you just made money. It's still the same amount of time. What changed? Just how many times a year the interest is being compounded, just the compounding frequencies, guys, okay? The fact that they are compounding the interest, so when you compound the interest, you're not calculating the interest just on the principal, you're also calculating on any interest you've earned. Because of the compounding effect, this money has just earned you an additional $2.42. I know some of you are saying, well, what am I going to do with $2.42? You could go to McDonald's and buy two Big Mac, but that won't even afford a Big Mac, okay? 2 double cheeseburgers, 2 McChickens, or for me, it's about buying gas. This could get me a gallon of gas, okay? So the $2.42 makes a difference. But this is only on 2,000, guys. What if you had 10,000? What if you had 100,000? What if you had $500,000 or $1 million? Okay, you see what I'm saying? So anyways, guys, let me keep going. Let's this time do it monthly. Let's go to monthly. If we're to take the same amount of money, guys, the same amount of money, and compound the interest monthly, okay? On a monthly basis, same amount of money, but the compounding frequency is changing. The length of time is still 3 years, guys. We're gonna go to that large formula and we're gonna plug everything in. By the way, guys, if you've got your calculator, you should practice with the calculator that you're going to use on the test, okay? Don't wait until the test to practice with your calculator. So 2,000, open parentheses, 1 plus 0.02, and then we're going to, ooh, Shazam, I forgot to divide it by, hold up a second, let's go back, I left something out, 0.02 divided by 12, because guys, monthly is 12 times per year, and then I'm going to raise this to the 12 times 3 power. Now, let me say this, guys, on a side note. When I'm doing these problems on a calculator, what I like to do for the power is to go ahead and do my multiplication ahead of time. So that 12 times 3 power, rather than plug into the calculator 12 times 3, I am going to use the 36 power, guys, okay? So when I type it into my calculator, hopefully you guys are listening, I would do 2,000, open parentheses, 1 plus 0.02 divided by 12, close the parentheses, hit your power button, guys, and raise it to the 36 power, okay? Now, I'm typing it in exactly like I see it. The only difference is rather than using the 12 times 3 power, I'm using the 36 power, guys. So the amount of money I have accumulated, if the interest is compounded monthly, guys, for the 3 years, is $2,123.57. You see, guys, listen, the more times the interest is compounded per year, the more money you will earn on your investment. So one more, and then I'm gonna leave it alone. This time, guys, we're going to compound the interest continuously. If we're compounding the interest continuously, there's no end value. So we can't use that large formula. Rather, we use the PERT formula. So in the PERT formula, we're going to plug in the 2,000 for P, and then we're going to raise it to the 0.02 times 3 power. Now this one, it's okay. The calculator will prompt you to plug in the power in the form of 0.02 times 3, guys. So on your calculator, guys, if you've got your calculator, you should be practicing. You should do 2,000, and then hit your second key or your shift key, and then hit the LN key. And guys, you should see the LN key. Normally it's on the left side of your calculator. If you got one of those unusual calculators, it might not show up, but you should be able to find the E button on there. And the E button should look something like this, okay? So look for it. Usually it's above LN, okay? And then once you hit the E button, guys, you will notice it comes up with the parentheses automatically, waiting for you to insert the exponent. So 0.02 times 3, and then go ahead and close off the parentheses. So you get A is equal to $2,123.67. I know some of you are saying, well, wait a minute, that's just an extra 10 cents. But guys, every penny makes a difference, okay? 10 pennies equal a dime, 10 dimes make a dollar, people. Every penny makes a difference, okay? So guys, the best way to get the best bang for your money is through the power of interest being compounded continuously. So the more times the interest is compounded per year, the more you earn on your investment. All right, so now here's the big question. For those of you looking at this and saying, you know what, that's $2,000 in 3 years, that's not enough money for me. So the big question for you guys is this: is there a way, can I invest this money into something else and make more than $2,123.67? Is there a way for me to make more than that, guys? What are some ways we can make more money than that? Drop it in the chat. Anything? Nothing? Oh, geez. Are you guys there with me? All right, guys. So here's some options, okay? You could do a CD account. Now, a CD for 3 years, guys, I probably wouldn't do it, but a CD, for those of you who don't want to risk your money, is an option where you lock the money away for a certain period of time, anywhere from 3 months up to 5 years, and they will give you a better rate of interest on the money, okay? So a CD, if you got some kind of business, you can invest it in a business. There's also what's called crowdfunding. Crowdfunding, this is where they raise money for real estate projects, something like that. And you can go into crowdfunding for as small as $500. Some of you may be saying a bond. Yeah, you could do a bond, but bonds don't pay that great. The interest rate is horrible. Or for most individuals, guys, they would prefer to put it into the stock market. And so I just want to mention this, guys. The stock market is very risky. It is not guaranteed by the federal government, okay? So you could lose all or some of your money, but there's a possibility that you could make great money from your investments in the stock market. So guys, if you have that $2,000 and you don't need it for the next 3 years, you could take that money and invest in the stock market. The easiest way, I like to call it the lazy way of investing in the market, is through what we call index funds. And one of the most common index funds is the S&P 500. And typically, it has an average rate of return of 7%. You just put your money in the index fund and just let it ride the market. I think right now, I think I saw it this morning or this afternoon actually, the shares of the S&P 500 were trading for about $326 a share. So you could take that $2,000 and put it into the market in the S&P 500 and let it ride the market, guys, for the next 3 years. And who knows, you might have a year like this year where the market did exceedingly well and you bought it like right when the stock market was at its low. So your money could actually, you know, double, okay? So that's one way to do it. And then another way to do it is through individual stocks. And so last year in one of my classes, my MGF 2107, we do have a chapter on investment. By the way, guys, this is the right time for you to start registering for your courses. I talked to you about this last week. So I'm going to mention again, if you haven't signed up for your spring courses, consider signing up for your spring courses. MGF 2107 is an easy class to take, and you do get a math credit for it depending on your major, okay? Easy math class, guys. So anyways, back to what I was saying. So I had a student in the fall last year who took me, and I was talking about the investments, guys. I was in the investment chapter, and I was talking about investing in the market. And so she decided to take $200 and drop it in the market. One of the stocks she bought was NEO. NEO, when she bought it at $1.57 a share. I think she said she bought 30 shares of it, and the 30 shares ended up costing her $47. So she sent me this email 2 weeks ago to the day, and she's like, you know, that NEO that you were talking about, when you were talking about the investing section in that chapter. It's doing so well for me. Right now, I've made over $1,000 off my $47, guys. So she dropped $47 in the market, and now her $47 is worth $1,000. At the time, NEO was trading at $34 a share. Today, before I started class, NEO was at, I think, $48 a share. You guys can look it up. By the way, anybody know what NEO is? Does anybody know what NEO is? Nobody? Okay. So NEO, guys, is an electric car company out of China. It's like the competitor to Tesla, but it's in China, okay? So I say this to you guys because there are ways for you to grow your money. Obviously, we're talking about exponential growth here. There are ways to grow your money. It doesn't necessarily have to sit in a savings account, okay? You can drop the money in the market. Is anybody in here invested in the market? Anybody? Raise your hand if you're invested in the market. Anybody? No, but I plan on it. Okay, Maddie. Anybody invested in the market? Oh, wow. Okay. Jennifer says, yes, I am. Okay. Anybody else? Okay. Awesome. Okay, just one person is invested in the market. Wow. All right, guys. Well, the process is easy. If you want to know how to do it, guys, it's easy. I can share some of my public accounts with you and show you a thing or two about how to navigate these apps. I don't have a problem with that, okay? I had my kids buy Disney stocks. Nice. All right, Jennifer. Nice. And Disney's doing well today. Disney, I think, was at $144 today. Oh, that's awesome. While I'm on this, guys, Tesla was just added to the S&P 500. They're adding Tesla to the S&P 500. Yeah. So that's a big deal for Tesla. All right, everybody. So let me stop talking about stocks so much. If you want to know a little bit more, you're welcome to go ahead and hang out at the end of class. I'll go ahead and talk to you about it, okay? Lesson 4.2 is what we're moving on to, guys. And we're talking about the logarithms, okay? Now for the logarithms, guys, this is how they come about. Remember, we're talking about the exponential functions. F of x is equal to, let's say, 2 to the x. We can also rewrite this as y equals to 2 to the x. Remember, f of x and y are the same thing. If we were asked to find the inverse of this exponential function, remember we talked about inverses back in chapter 2. We would go ahead and swap, take our equation, y equals to 2 to the x, and swap x and y. So the equation would become x equals to 2 to the y power, and then we would have to solve for y. So guys, here's the conundrum. The y is in the power. How in the world do you solve for y when it's in the power? Okay, so this is where the log function comes in to solve for y. So we take this equation right here and rewrite it. Now, guys, I am going to be sharing an acronym with you, so hopefully it helps out some of you. X represents the answer, okay? Y represents the power, and 2 represents the base, okay? So when we take this, we convert it to log form. We rewrite it in log form. It's going to be the log. By the way, this is the writing line right here. Notice the log goes directly on the writing line. The base, which is the subscript, guys, so it goes below the writing line. Log base 2 of the answer, which is x, is equal to the power, which is y. So essentially,
you said x is answer, y is power, and what is base?
I'm going to tell you. Hold on a minute. Okay. We just solved for y, guys. So y, which represents the power, is equivalent to log base 2 of x. So when you're evaluating these logs, when you're solving the logs, you're basically looking for the power. So basically, the logarithms, they are the inverses of the exponential functions. Logs, that's the short form for logarithm. Logs are the inverses of the exponential function. So guys, here's the acronym, just in case, okay? 2 is the base. X is the answer. And then Y is the power. So the acronym is BAP. Base, answer, power. So we're gonna BAP the log. BAP the log. Base, answer, power. This helps you to remember where each portion is placed when you are rewriting these problems in log form or in exponential form. Yeah. So hopefully the acronym helps out somebody, guys, okay? So guys, let's look. I am going to convert some of these. Convert exponential equations to log form. So we're going to convert from exponential form to log form. So guys, here is an exponential equation. 5 to the third power is equal to 125. We're going to rewrite it in log form. So in log form, it's going to be log base. What's the base? 5 of the answer, 125, is equal to the power, which is 3. Base, answer, power. Okay. Now, here comes another one, guys. This time it is 9 to the second power is equal to 81. And again, remember it's base, answer, power. So when we rewrite it in log form, it's going to be log base. What's the base? 9 of the answer. What's the answer? 81 equals to the power or the exponent, which is 2. All right, so now we're going to do it in reverse, guys. We're going to convert from log form to exponential form. Now let's convert from log to exponential form. And of course, be careful where you place those components, guys, okay? So here's the first log equation. Log base 4 of 16 is equal to 2. Now we're going to rewrite this as an exponential equation. The base is 4, the power is 2, and that's equal to 16. Here's another one, guys. Log base 3 of 81 is equal to 4. So here we go. 3 to the 4th power is equal to 81. The base is 3, the power is 4, and the answer is 81. Any questions, guys? If you don't have any questions, I am going to erase yet. No, I'm not erasing. You good? You good? You good, Jennifer?
Yes, ma'am.
Okay. So now, guys, let's evaluate some of the logs. We're going to evaluate the logs. So when you're evaluating the logs, guys, what you're looking for is a power or the exponent. So just keep that in mind. We're looking for power or the exponent. I'm going to start with something easy. Number 1, we're evaluating log base 2 of 8. So this one is asking 2 to the what power gives you 8. 2 raised to the what power gives you 8. 2 multiplies by itself how many times to give you 8? That's the question. Yes, Maddie, that would be 3.
3.
So that's it for that one. Number 2, log base 4 of 64. 4 to the what power gives you 64? This is not division. You cannot do 64 divided by 4 and get 16. No. 4 multiplies by itself how many times to give you 64? That's the question, guys. Yes, that one would be 3.
3.
Number 3, guys. Log base 7 of 49 is equal to what? 7 to the what power gives you 49?
2.
That would be 2, okay? So when you're evaluating the logs, you are looking for a power or an exponent. So let me give you some that are a little bit more challenging, okay? So here they go, guys. Number 4. Log base 5 of 1. 5 to the what power gives you 1?
0.
It is 0. Number 5. Log base 36 of 6. Ooh. Log base 36 of 6. The base is larger than the answer? Yes.
-6.
No, not a negative. Okay.
1/6.
I got where you're going, but it's not 1/6 because you're doing division there. Okay. And we're not doing division, we're doing powers. So 36 raised to the what power will give you 6. So the question you should really ask yourself is, how can I go from 36 to 6 besides division or subtraction or multiplication or something like that? How do I go from 36?
0.5.
We'll say it again?
0.5.
0.5.
1/2.
Yes, that is correct. 0.5. You're all right. Very good. Okay. So guys, one of the ways to go from 36 to 6 is to go ahead and take the square root of 36. And the square root is the same thing as the half power. Yeah. So this one is 0.5. Now, additionally, let me work it out for you guys. Remember, we can easily convert these logs to exponential equations. So if we were to convert this one, we would rewrite it like this. 36 raised to the what power gives me 6. If I factor 36 into a base 6 number, this would be 6 to the 2x power equals to 6. Now, since the bases are equivalent, we have this 1-to-1 property that says if the bases are equivalent to each other, then that means that the powers are equal to each other. So if x to the m is equal to x to the n, then this means that m would equal to n. So guys, the bases are equal. That makes the powers equivalent to each other. So you divide both sides by 2 to get x equals to 1/2. Yeah.
You completely lost me.
I lost you?
Completely.
Okay.
I got the square root of 36.
Right?
Well, it's supposed to be 6. I'm not sure where you got 36 over 1/2.
Okay, because the square root is the same thing as the half power. Okay, scratch that. How about this? Down here, I factored 36 into 6 squared. Okay with that? 36 is 6 to the second power. You all right with that? Okay, you're not all right with that. So that means that you're not all right with the equation right here. Is that the problem?
No, I know 6 squared is 36.
Mm-hmm. Okay, and I'm setting this equal to 6 because I just converted this. This is the base. That's the answer. This is supposed to represent the power. So if I take this equation right here and rewrite it in exponential form, it would be 36 the base raised to the power, which we don't know, we call it x, is equal to the answer, which is 6. So I factored 36 into 6 squared. We already had the x power there. So on the right side, you have 6, and if you take 6, you raise it to the 1 power, you still have 6. And then there's a rule that says when the bases are equal, the powers are equal to each other. Remember, this is an equation. So essentially, when you're dealing with an equation, whatever you have on the left side must equal to the right side. That's what an equation is, okay? So if the bases are equal, then the powers have to be equal to each other in order for the two sides to be equal to each other. So if that's the case, then that means that the 2x would equal to 1, and that's what I dropped over here, and then I solved it. If 2x is equal to 1, then that means x would equal to 1/2. Hold on to that thought. We're going to see these again later on, okay? So hold on to that thought. Okay, guys, here's another one, okay? Now, pay careful attention to this one. That was number 5. Here's number 6, guys. This one is log base 8 of 1/2. What is that one equal to? 8 to the what power gives you 1/2? Ooh. 8 to the what power gives you 1/2? Nobody? Okay, now earlier at the beginning of this, guys, we were talking about the exponential equations. Remember I said, whenever you encounter a negative exponent, think of a fraction. So this is the reverse of it. There's a fraction in there. So I must think about a negative exponent. So basically, 1/2 to the what power would give me 8. Or you could look at it this way. 2 to the what power would give me 8. That would be 3, but then I need to change that to a negative because of that fraction in there. Are you guys okay with this one? What's the answer? It's a negative, guys. What's the answer?
-3.
-3, man. Very good. Yeah, -3. Okay, so it sounds like I'm stumping you guys right there. I feel like I'm losing some of you, okay? Remind me, guys, I gotta show you how to type these on the calculator. Yes, something like this, you can plug it on the calculator. So if you didn't get that one, hold on to it. We'll go over it in a little bit, guys, and I'll show you how to plug it into the calculator too. Now, one last one, and then I am going to go ahead and move on. This one is going to be log 1/2 of 16. Okay, 1/2 to the what power will give you 16. Very similar to the previous one, yes. Okay, 1/2 to the what power will give you 16. Remember, there's a fraction in there. When you see the fractions, you should be thinking of a negative exponent.
-4.
-4, yep, okay? Because 2 to the 4th power is 16, but because of the fraction there, it becomes a negative, okay? Now, later on, guys, when we talk about this some more, it'll make more sense to you, okay? So let me go ahead and drop some of these basic properties of logs. Properties of logs, guys, basic properties of logs, okay? So we're going to start with the basic properties of logs, which allows you to simplify the log size. Now, as we go through this, remember everybody, okay, we're just evaluating these. And when we talk about these properties, guys, we're looking for what? The exponents. We're looking for exponents, okay? So guys, here's the basic properties of logs, okay? So here's one. Number 1, log base b of b. B to the what power will give you b right back, or be 1. Now, if that's not making sense to you, let's look at this concrete example. Log base 4 of 4. 4 to the what power will give you 4. That's 1. Okay. Number 2, log base b of 1. B to the what power will give you 1. That would be 0. Again, let's look at a concrete example. Log base 4 of 1. 4 to the what power gives you 1? That would be 0, because anything raised to the 0 power is equivalent to 1. Now, number 3, guys. Log base b of b to the x power is going to simplify to x. And then there's a number 4 that is very similar to this one, but be careful how you write it. It's b to the log b to the x power, and this one will also simplify to x. Now, these two right here, they're inverses of each other. They're practically the same thing. So guys, pretty much here's an example. If you have log base 4 of 4 to the second power, this would simplify to 2. Think about it, guys. 4 squared is 16. 4 to the what power gives you 16? 2. Just like that. So that's the first set of properties of logs, guys, the basic one. Now, here's another set of properties of the logs. We call them the common logs. Now, when we speak about the common logs, guys, we're looking at log with no base. When the log is written with no base, it is understood to be base 10. So if you see the log written with no base, it's understood to be base 10. So if you see something like this, log 100, there's no base, it is understood to be base 10. So this is the same thing as saying log base 10 of 100. 10 to the what power gives you 100? 10 multiplied by itself, how many times to give you 100? 2 times, okay? So guys, when you have the log with no base, the base is understood to be base 10. So log 100 gives you 2. Now, here are the rules for this one. Log 10 is equal to 1. Now, why is that? Because 10 to the first power is 10. Number 2, log 1. 10 to the what power gives you 1? That would be 0. Number 3, log 10 to the x power will just give you x. So it just simplifies out to the power. And then number 4, 10 to the log x. This one will simplify out to just x. And guys, that's it. So, any questions? No questions? All right, I've got another set to go through with you guys, okay?
I have a question.
Mm-hmm.
Is 3 and 4 also an inverse of each other as well?
Yeah, absolutely. Okay, one more set. Okay, here's the other set, guys. This time it is the natural log, guys. The natural log. When we talk about the natural log, we're looking at ln. In some of your textbooks, as well as on the calculator, sometimes they use capital ln. It doesn't matter, capital or lowercase, it doesn't matter, okay, guys? So when we talk about the natural log, we're looking at log with base e. So instead, remember earlier we looked at the e value, guys. When we look at anything involving the e value, we're looking at things that are naturally occurring, exponential growth, exponential decay, which we'll cover later on, okay? So here, guys, rather than writing the log with base e, we switch this, or we convert this to natural log. So you have to understand the natural log is simply log with base e. So here are some rules that goes along with the natural log, guys. Number 1, natural log e is equal to 1. Now, if that doesn't make any sense to you guys, think about it this way. If natural log represents log base e, you can rewrite this as log base e of e. So e to the what power gives you e right back? That has to be 1. Okay, number 2, natural log 1 is equal to 0. Remember, anything raised to 0 power is equal to 1. Number 3, this is the one that you're going to see Natural log E, guys, is the one that you need to memorize. You will see this most frequently, but this is the second one you will see very frequently. Natural log of e to the x. This one, the power is just going to simplify out, okay? Because the natural log e cancels out, so you're just left with the power. So likewise, this leads us to number 4, which is e to the natural log x. So this one will simplify out to just x. Any questions on this one, guys? Any questions?
Can you repeat number 4? What is the?
E raised to the natural log x. Just simplifies to x.
Okay, then.
All right.
Will you be showing us how it?
Yes, absolutely. I will. I will show you how it simplifies out. Okay. So let me go ahead and run through some examples with you guys for this particular section right here, so that when you see these problems, you're familiar with them. Okay, so here's some examples, guys, of how you're going to see these, okay? Let's say they give you something like this, natural log e to the 7th, and they ask you to simplify this, natural log of e to the 7th power, okay? Well, that's one of the rules here. If you go under the natural log section, that's rule number 3. It says when you have natural log e to some power, it just simplifies to
7.
Yeah. Number 2, this one right here, if you have log 1,000, and remember when you see the log with no base, the base is understood to be base 10. So this one is asking 10 to the what power gives you 1,000. By the way, guys, you can type this
100.
into your calculator. What did you say, 100?
Yes.
Okay, if you were to multiply 10 by itself, how many times would you multiply it by itself to get to 1,000?
Oh, twice. No, 3 times.
3
10 times 10 would be 100 times 10 would be.
Right, right. Okay, remember, these are all exponents, guys, okay? So here's another one. Now, this one, very similar problem, but it's a decimal, guys. What did the decimals represent? Fractions. This is log of 1/100th. 1/100th as a fraction. So, since we have a fraction, what kind of answer are we expecting? We're expecting a
Negative.
negative answer. So what would it be?
-2.
-2, absolutely. You got this, man.
I just got a calculator.
I love it, I love it. All right. Log,
Honest, man.
say it again.
He's honest.
Yeah, absolutely. Log of 10 to the 9th power, guys. And again, this is one of the rules. It just simplifies to 9. The power comes out because log 10 is 1. Let me see here. Let me clean out this part right here. Here's another one. Now, I didn't mention this earlier, but I'm going to go ahead and mention it in a little bit. I forgot what number I was on. But log base 4 of 4 to the x squared, guys, this one is just going to simplify to x squared because the log base 4 of 4 simplifies to 1. There's a reason why. I will show you guys why in a little bit. It's already 7:48. Yeah, that will take us to where we can go ahead and talk about it. All right, guys. So here's the last one I want to mention. Natural log of e to the square root of x. You will encounter these problems where you have to deal with the roots, the radicals. So on a side note, guys, let me go ahead and go on the side. I have to mention this. Earlier, I mentioned that the square root is the same thing as the half power. Sometimes they do expect you to convert the radicals to a fraction or exponent or a rational exponent. Not all the time, certain cases. Like in this case right here, you do not have to convert it. In the next section, you're going to have to convert it, okay? So this one right here, natural log e to the square root of x, the natural log e cancels out, so that leaves you with square root of x, okay? Now, additionally, let me throw this one in here, guys. If you have the cube root of x, this is the same thing as x to the 1/3 power. And if you have the 4th root of x, this is the same thing as x to the 1/4 power. Okay? So you have to know how to convert from radical form to fractional exponent form. Okay? All right, guys. So now let me go ahead and do this. And I am going to start the next lesson, but we're not going to be able to finish it. Let's solve some equations, guys. We're going to solve some equations now. Log base 3 of x minus 1 equals to 2. Now, they want us to find the value of x, which reminds me, I forgot to talk about the log graph stuff. We got to talk about these log graphs, okay? I don't think I'm going to be able to get to it tonight because I'm running out of time. It's almost 8 o'clock. I'm going to have to stop at 8 o'clock. So remind me next time we meet, guys, to talk about the log graphs, okay? So here's a log equation, guys. They want us to find the value of x that would make this problem true. Remember, this is the base. That's the answer. That's the power. So what you do is you convert it to an exponential equation. So the answer, x minus 1, is equal to the base, 3, raised to the power 2. So there's your equation. So x minus 1 is equal to 9. And then you add 1 to both sides. So you get x is equal to 10. Does it make sense? Of course it makes sense. 10 minus 1 is 9. Log base 3 of 9 is 2. Yeah, it makes sense if you plug it back in to check it. All right. Oh, guys, remind me, before you go, I have to show you how to type these into the calculator, okay? Number 2, guys, look at this next one. Log base 5 of x plus 4 is equal to 2. Very similar to the previous problem. Base, answer, power. So when we convert this, it'll be x plus 4 is equal to the base, 5 raised to the power 2. So we get x plus 4 is equal to 25. We subtract 4 from both sides. So we get x is equal to 21. Any questions, guys? All right. Sounds like you guys got this one. Log base 4 of x equals to -3. Again, guys, this is your base. This is your answer. That's your power. So convert it. So the answer is x. It's equal to the base, which is 4, raised to the -3 power. Anything raised to a negative exponent becomes a fraction. So this is going to be 1 over 4 to the third. 4 to the third is 64. There's your answer. All righty, guys. Now, here's one that's a little bit more challenging. Log base 3 of log base 7 of 7. Now, this one requires the use of order of operations, which says do what's inside the parentheses first. So in the case of this problem, you want to simplify what's inside the parentheses. Log base 7 of 7, guys. What's log base 7 of 7? 7 to the what power gives you 7. That would be 1. Then you simplify this. 3 to the what power gives you 1. That would be 0. So that's the answer, guys. Did you get that one? Oh, look at you guys. You guys are like, I'm not sure I got that one. Here's another one. Try this one on your own. Log base 2 of 32. Try this one, guys. Log base 5 of log base 2 of 32.
1.
Yes, very good. So guys, you calculate log base 2 of 32. 2 to the what power gives you 32? That would be
5.
5. Okay, I don't need the parentheses there, but for some reason I put the 5. I mean the parentheses there. And then 5 to the what power gives you 5? That would be 1. Very good. All right, guys. It's like almost 8 o'clock. I'm about to stop. But Maddie had the question earlier. So how would I be able to simplify those rules, those properties? How do they come about with some of these answers to these properties, okay? So in the next lesson, guys, I'm not gonna go through the entire thing because we're running out of time. Lesson 4.3 has to do with the properties of logs to condense or expand the logs. So we're going to use these properties to expand or condense the logs. There's 3 of them, guys. One of them is the product property. I'm not going to go over that one right now because we're running out of time. In the product property, guys, remember, the logs, they're inverses of the exponential function. So basically, the logs are just exponents. Remember the exponent rule that says when you multiply with the same base, what do you do with the powers? You keep the power and you keep the base and you add the powers. So this is the same thing. When we talk about the logs, the product becomes a sum. We'll talk about it next class. The other one is the quotient property. And that goes back to the rules of exponents too. That says when you divide with the same base, what do you do with the base? I mean, what do you do with the powers? You subtract the powers. So with the logs, when we talk about the quotient will become a difference, okay? We'll expand on that next week, guys. This is not all of it. We'll talk about it next class, okay? Now, the one that I really wanted to get to, guys, is the third one, the power property, because I need this to explain some of the rules from earlier. The power property says this: if you have log base b of m raised to a power, the power, here, let me use a different color, the power becomes the coefficient of the log. So you can rewrite this as p times log base b of m. So once again, guys, when you have a power, the power becomes the coefficient of the log, okay? So why do I show this to you? Because of those properties from earlier. So here's one of the properties you guys saw. Natural log e to the x power simplifies to x. Why is that? Because this is a power. The power becomes a coefficient. So you'd have x times natural log e. And you know natural log e simplifies to 1. So basically this cancels out, leaving you with x. Likewise, if you have log 10 to the x power, the x becomes the coefficient. So this would be x times log 10. And you know log 10 is equal to 1. So this cancels out, leaving you with just x. We saw this one earlier, guys. Natural log e to the square root of 7, to the square root of x. Same thing. The square root of x becomes a coefficient. So you have the square root of x times natural log e. Natural log e cancels out, leaving you with square root of x. Okay? So this property right here explains why we had those basic properties from earlier, guys. So that's why I wanted to get to this one right here. The other 2, I did not go over them. I will go over them in class, by the way, okay? So when we meet next week in class, I will definitely elaborate on them and go over them in detail. So I am going to go ahead and stop here, guys, because it's already 8 o'clock. and I don't want to keep you guys for too long.
Don't forget attendance.
Yeah, I'm going to do that. And so let me go ahead and stop this recording right here.